Alright, I think that one has sound, I just don't know how good of sound it is. So, we'll go with that for now. I'm not even sure which one it is that's capturing sound. So it might not sound that great until I figure out what is the deal. What we're going to do today, actually, I was going to talk mostly about filament and things like that. So, like, how is the filament made, the additives that can be in the filament. I do have the printer running over here. I'll probably shut it off. I just wanted you to see, although now the sound might be kind of weird, so let's see if we can make the sound work on it. Now I guess it is. I have it running as a copy mode print, just so you can kind of see if the you know, what it looks like when it's in copy mode. These are the same two filament. They're just PLA red and blue that we used when we were making this guy last time. Actually, the last time we were live. The last two were pre-recorded because I was at that workshop. And one of them was about topology, which is a piece of software that you may not have ever even heard of before, but it is a if you watch that video, it's a CAD software, but it works completely different from SolidWorks, Fusion 360, Tink. It works all of those different software packages that you might have seen before. Unless you had seen topology, you haven't seen anything really like it, I assume. It is very different from the other types of software out there. Let me go ahead. This is just printing two bases so you can kind of see how it does. If it was in the duplicate mode right now, if it was in the mirror mode, then it would be doing basically the same thing, except this extruder would be mirroring what the other one was. And you get two copies of the same thing, but one would be a mirror image of the other one. And so it's a useful-ish feature, particularly if you have things that need to be mirror imaged, and you don't want to go through the process of creating the CAD, the geometry mirrored, which isn't that hard. There are online tools that you can just mirror STL files. But if you just wanted to have one file and print it, one copy, a left and a right version, for instance, then that would work. These are exactly the same copies, other than different materials. On these IDEX printers, that is one thing that you can do differently than on other printers that can do multiple materials. This one, the two materials can be completely different. So you can have a a PLA in one and a TPU in the other one, because the nozzles, the extruders, everything are completely separate. So you can have different temperatures and everything per nozzle. So that's useful. These are both just PLA. They're actually really close to finished, so I might just let them finish. They've got a few layers left. This screen doesn't actually give you a percent or a time remaining. It's just a bar graph, and it's almost at the end. And I can just tell that they're pretty close to finished anyway. So I might let them finish just because they're so close. This printer, one problem with it is a hardware issue where this bed, now it doesn't come with the glass bed. You can't see it on here, but I've got a Creality bed on top of the metal bed that it comes with. And for whatever reason, and I guess it's because it's a larger bed, they decided that in the center here, right in here, they needed to put a standoff. So underneath it, there's a little metal standoff that kind of is a little bit too tall. And so the center of this bed is bowed up compared to the rest of it. And that creates a pretty big problem with getting the bed level. So I need to go in there and undo that. There it finished. Need to go in there and undo that. I'll let it park and then I'll shut it off. Alright, just because the fans on it are so loud. So maybe you can hear better now. I still am not sure what microphone is picking up the sound. think it actually might be the microphone that's looking at this. I'm not sure, because I don't have any others that it might be picking up sound from. So I'll leave that on, and maybe I'll move it closer to me instead of way over there. We'll do that. How about, and kind of see what it's doing. So anyway, the bed on this printer does have a hump in the middle of it because of that standoff in there, and so it makes the leveling of it really complicated. In fact, this one doesn't even really have a bottom on it on this print, because the nozzle was so close to the bed that it just couldn't extrude filament. So I'll have to work on that a little bit. Other than that, the printer is working pretty well. It's still, I think, probably if you wanted or needed an IDEX Independent Dual Extruder printer, it probably is the cheapest one that you're going to get that works well enough, but it does need some work. This is the JG Maker Artist D. There's a pro version that's slightly better, but I don't think any of the hardware is particularly different. I think it's just the software, and the screen, I guess that's hardware. The screen is different because it's a touch screen. But there are some issues with this, and I don't know if there's a particular use for an IDEX printer. I guess if you were printing two color parts or two material parts in particular, that is one good thing that this can do. In the early consumer days of 3D printing, so not the industrial days in the 1980s and 90s, but when people, just ordinary people, could go buy printers, the slicers hadn't at that point figured out that you could just use your model material as support material, and the support at that time was really only done with a separate material. So you had two different materials being delivered to the printer, which usually meant two nozzles, or it always meant two nozzles back then. And one of those materials could dissolve in like a lye solution. Now they have some that dissolve in just water. And so that's still a viable option. Maybe you have really complex geometry that you need FDM printed. So you need this process, but you have really complicated geometry. And the support material, just clicking on support in Cura, is not ideal. It's really hard to remove. It's everywhere. It encases your model or whatever. So it's a really time-consuming thing, and that's the only way to get the part printed. Another option, this would be a reason to get an IDEX printer, is that one of these nozzles, now they're off the screen now, I guess. There's the end of it. Let's see if we can, there it is. One of these nozzles could be loaded with a material specifically designed to be support material that's easily removed. And easily removed means that it dissolves somehow. So there is a PVA, like the PVA Elmer's glue type of stuff, that you can print, and it can be dissolved in water. So if you did have a printer with two extruders, one could be your model material, so PLA, PETG, ABS even, although this printer would probably struggle with ABS just because it's an open air printer. So PETG in here and PVA in here, they do the alternating thing. Your model is only one color, but the other filament is the removable support, dissolvable support. So that is a reasonable option, or a reasonable reason why you might want one of these dual nozzle printers. They do have some where they're not independent, so they're made on the same carriage. There are some printers like that still. Then the reason to get that particular printer is usually cheaper, although not necessarily cheaper than this particular printer, because it's kind of going out of style right now. So you probably get this particular one relatively cheap. But there are some dual nozzles that aren't independent. I think the independent one is probably a better option if you need to go that route anyway, because you can do other things with it also, like you can do the copy mode or the duplicate mode, and that's really limited. Well, you can't even, or I meant copy or mirror. You can't even do the mirror mode if they're connected together here. But you could at least copy really tiny parts on the dual extruders where the carriage is connected together. They're not independent. They just have to be really small parts to do that. So those are some reasons why you might want to do the dual extruder, dual independent extruder. So I'm going to play around with this one a little bit more. It's really large, so it takes up a lot of space. Though, if it wasn't large, then your independent dual extruders are, they're kind of getting in the way of each other, and you can't print big parts. So it typically is going to be a larger printer. So it does take up the whole desk over here. That's why I normally don't have it out. It's normally out away somewhere. All right. So enough of that. Let's go to Cura real quick because I did have something I wanted to show over there. Wow. The chat got covered up when I clicked on Cura, and I just now saw that the sound wasn't on over there. Didn't think about that. In fact, before I forget, let me, well, maybe I just won't change off of this particular mode. But all I was showing was I was showing fuzzy skin in Cura for the past 5 or 6 minutes where you couldn't hear anything. So all I was saying is that fuzzy skin is a modifier to your STL file itself. So it doesn't actually change the geometry. It just changes the G code generated from the file. So it's sort of like when we used Idea Maker to put a pattern on the model, the STL file, without actually changing the model itself. Fuzzy skin is only in Cura as far as I know. I don't think Prusa Slicer has a fuzzy skin. I guess Idea Maker sort of has a fuzzy skin, but it's more of a pattern that gets embossed on it. And I was just showing some of the features here. One thing I noticed that when I flipped between vase mode, spiralized outer contours, and just printing one wall is that for one reason or another, Cura won't do both spiralized and fuzzy skin. So not sure why, but it would do the vase mode, but it wouldn't do the fuzzy skin on top of the vase mode. So I had to go back and I had to switch to one wall, no top, no infill, and kind of create my own vase mode. It's not the same as vase mode though, because vase mode does create a helix when it prints. So this is one layer after another stacked on top of one another here. So it's slightly different. Does take a little bit longer than vase mode. Well, the reason it's taking longer is because all the extra movements it has to make to create the fuzzy skin. And then where we were, so that catches us up to about where we were, is I was saying that it's kind of difficult to control where the fuzzy skin happens, but there's this modifier on the left hand side of Cura where it's per model settings, and it may not be easy to control. At least I don't use it very often for this, but you can have a fuzzy skin that only gets applied to certain parts of the model. So for instance, let's see if we can make this happen. Let's add in a just a cube. Let's not get too worried about it right now. So let's see if we can get them not on top of each other. So there's our little cube, and let's scale it somewhat. Let's say that, well, let's scale it only in one direction. And let's make it, let's basically make half of, let's see if this works. So I've got this cube, I'm not going to print the cube, I'm going to use the cube as a per model setting. So basically wherever this cube exists, it's going to do a certain thing to the model. So what I want to happen is for the overlap between my, I guess it's not a cube anymore, my block and the vase, I want that to be fuzzy and the other half to not be fuzzy. That's my goal. So if we sliced it right now, it would just print some weird, I don't even know what it would print. Let's see. It'd print this. So I've got one wall, so it's kind of not doing exactly what I want at all. So let's not do that. Now let's go back over here, and I don't remember which one I need to select. I'm going to select the block, per model settings, and I want to select my fuzzy skin settings. Oh, well. And I'll leave these alone. These are the modifiers for making the fuzzy skin either more lumpy or less lumpy. You know the how fuzzy is it basically. So I'm not going to worry with those. Okay. Let's turn off the global fuzzy skin, and now I think, well, let's slice it and see. Not Oh, we need the intersect. Okay, okay. All right. So we need modify settings for overlaps. So can we modify? Yeah, we can. All right. Fuzzy skin is on the overlap. Let's see if that's what we want. Well, it doesn't look like it actually applied it. I wonder if we're supposed to do the opposite. All right. I never can remember. I don't use these settings often enough, but I might need to select that one, or maybe I just need to select both of them. No, it has to be all right. So I have to do one of them. Let's see, modify settings, don't support overlaps, print as support. This button lets you can build in your own little supports if I wanted to. Let's see if that, okay. Oh, I've got them both as modifier meshes, so I can't do that. Actually not sure how to there we go. So it can be the same thing, and I may have to work on figuring out the set of instructions to make it actually do what I want. And maybe it can't actually wall thickness. I wonder if I need to. Oh wait, no, that's for the model. I just want the overlap to be. There we go. All right. So you just have to do the. I had infill mesh. I needed to have cutting mesh selected. So here's the process and what you get. So maybe you want to control where the fuzzy exists on your model. So, now I do have a weirdness in here. I have this line through here, so it doesn't really kind of work on the, or at least it doesn't work this way on a hollow model, because it's going to put this in here. So a vase, it may not work on, but a solid part that's going to have infill or whatever, then it'll work on that. But we may have issues making it into a solid vase type model. But the idea is that you create a cutting mesh. Well, I don't know if you call it cutting mesh. They call it, was just a separate model. And then, so I made that block. Let's go back to what I made. I made that block, and I overlapped the block with the vase. And wherever the block overlaps the vase, I want that part to have one characteristic that the other part does not have. And you can add a bunch of these blocks, so that you can chop it up a lot of different ways. So I'm just trying to do half and half. So if I had a more reasonable model, so let's do what I would normally do: 2 walls, a top layer. Let's do 3 top layers, infill at my normal 20% or so. So there's my normal type of print settings. I've got an overlap block over here. I have set it as a per model setting, and I select it, per model settings, and then here's a modify settings for overlap. So anywhere my model, the block, overlaps the model I want to print, something's going to be different in that overlap. And I set it to cut. I don't fully understand the difference in infill mesh only and cutting mesh. I think that's so that if you want a higher or lower infill density in one region, we'll show you why you might want to do that in a second too. I still want to talk about polymers, but maybe we'll do this for a second. So infill mesh only modifies just the infill, I think, and cutting mesh does the perimeters, I think. And then you can select what you want to be different. So there's all these options, or you can type in some and find other options. So you can change the infill pattern or density. Do you want supports or not? Do you want it to print faster or slower there? More or less top, bottoms, or walls, and then you can search for other settings. And that's what I had to do. I had to search for fuzzy skin, and I clicked that. So when I slice it, I will get half of a model that is fuzzy, and half of it, well, I guess not quite half, but close to half of a model that's fuzzy, and half that is smooth. I do have this weird bit in here where it really did separate it into two separate models. I'm not sure if there's a way around that, because that does kind of make it a little bit odd that they're doing that part, but you could at least create a region that is fuzzy, or a region that's thicker or more dense or whatever, without having the whole thing that way, with these per model settings in Cura, without having to go and create separate models in CAD somewhere. Another reason you might do this is to add some strength around a part that needs maybe a bolt hole going through it, and you want to print a normal amount of walls on the whole part, like maybe 2 walls or 3 walls on the part, but around that bolt hole you want to have 4 or 5 walls. So you don't want to change the global setting of walls where everything gets printed with 5 walls. You just want them in that one spot. You could insert a cylinder right around that hole, do the per model settings for that cylinder. The intersection could be, hey, in this region I want to have 5 walls, and everywhere else I'll have 2 or 3 walls, and so that would be a way to use it in a more meaningful way than just a aesthetic way. Here you're not really doing anything other than make it look different, but that would actually make it perform differently if you had the per model settings increase the number of walls, or maybe you just increase the density somewhere. You have a part that needs one section of it to have a higher density than the other section, maybe for strength or maybe for weight even. You can do that. So those per model settings, it takes a couple of clicks around to figure out what you're actually trying to do. But like if I do the infill mesh, I don't think it'll do anything different because fuzzy doesn't apply to the infill. So it doesn't even split it up. So I don't think you would, you don't have fuzzy infill. All right, what I really wanted to talk about, that was almost an aside there. What I really wanted to talk about was just polymer filament in general. I've been looking, I've got all these samples of filament, and I saw this one. This one's antibacterial. So I don't even know if it's made anymore. It's an older filament. I didn't go try to look it up. Fiberforce.it. I don't know if that's still a thing or not. Let's see. Let's see. Have to make sure we have sound over here. Fiberforce. See if that's still a thing. Some of these samples are really old. It's still a thing. All right. And it is antibacterial, scientifically validated. It doesn't say what makes it antibacterial, but if you need an antibacterial, it even has an ISO rating, ISO 22196. I'm not sure. ISO 22196, was that it? We'll look at that later. 22196, yeah. See what that actually. Oh, it's just has to do with the plastic regulations testing. Well, antimicrobial. Here it is, 22196. ISO is a standards organization like ASTM or something. Fine. Everything has cookies. So this actually is the procedure for measurement of antibacterial activity on plastics and other non-porous surfaces. So they're serious here that they've got antibacterial PLA. I don't know how much it costs. Let's see. Products. Oh, this is its data sheet. So I don't know how you actually buy the stuff. Might have to, oh, you have to go to one of their distributors who distributes this stuff. These guys. FBRC 8 LLC in Bartlett, Tennessee. But so what that made me think of is, you know, there's a lot of things you can add in to your filament, and that made me think of well, all these additives, they could potentially affect the way it performs, and one of the additives is just color. So the way that color gets added to your filament before you print it is with this kind of stuff. So this is a color. Now this is the European spelling of color, but I just looked up a random master batch coloring for plastics. And these little beads here, these are pigments that are like little pellets that will get added into. You'll have another set of pellets like this, resin pellets, that are the bulk material, like just PLA or PETG or ABS or whatever your filament is. And you'll mix in like 2% or 3% of these to color it. So how filament is made, that's why I had this up. We actually have one of these. Actually, I think we have two of these. Two of these at school. These are very small, not great, but they do function. Filament extruders. So how to actually make filament. So there's much larger industrial scale versions of this stuff. Even these are $3,000. See the price there. So even these are not cheap. You can make your own. Even that's not going to be terribly cheap, and your results are probably going to be pretty varied on how it actually works. But these do work. We have made filament with them. We actually made some ABS filament that had ground tire rubber mixed into it. So used automotive tires ground up into like a powder, and then mixed in with the ABS, and it does change the properties generally for good, at least for anti-vibration type things. Obviously it weakens it, so it's weaker material strength-wise, but it has better anti-vibration characteristics when you mix in the ground tire rubber. Anyway, we use one of these things to make that. So you can make your own filament. So the process is, there's some kind of input for usually pellets. Recycling is a little bit different. We'll talk about that maybe a little later. But the pellets themselves are just whatever your material is. They look a lot like this. They look this, and they might even have color already added to them. So they might not be just you know, a natural color. It might already have color added to it. Or it might be that you get the natural color, ABS, PLA, whatever. But these are little pellets, and then you'll mix in 2%, 3%, whatever of this master batch. And there's master batch for color, and there's master batch for property. So if I go to the products here, you can see the additive master batch. Those will do the things like, well, like the antibacterial, although I don't think this company sells the antibacterial stuff. But you can go and get the silk additive or the matte additive. There's some, let's see, what do they have? Flame retardant, antioxidant, UV stabilizers, infrared barrier, you know, all kind of anti-fog, all these different things. These are not necessarily additive master batch for 3D printing filament. These are just for plastics in general. Some of them let you actually have one of these filaments where it will let the plastic part be laser marked instead of just melting the plastic. So I actually have one of those. I haven't ever tried it. Maybe I should try it someday. Anti-flame, so flame retardant stuff. Anti-static, I guess. But you can get those. There's some special effects you can get, and this is just one company's version of what the things might be. So there's a silk I don't know what unique effects means. Metallic. Looks like metal. That one's approved for food contact. So maybe you're making some spoons or whatever and you want them to look like metal spoons, but they're really plastic. Marble, all kinds of things. There's the lasered stuff. So all sorts of these little pellets can be added in to your raw material into a hopper, sort of like here, this little slot here could have a hopper of these pellets on it. There's usually a screw extruder here, so like an auger, looks like a sort of like a big drill bit, sort of, that's got a high torque motor. This little orange region here is a heater, so you will, and sometimes there's not a heater, sometimes just the auger itself provides the heat. I think all of these work with a heater though. And so the auger spins, or well, a motor spins the auger. The pellets are forced into this heat zone, and then I don't know if this one you can see the, yeah, this little output here has different nozzle. So if you want to make different size filaments, you might have a, the 3mm filament or the 1.75mm filament, or maybe you've got a reason to print some other size filament. Then this output would be tailored to that size. And so that auger is pushing filament through the heat zone. It's mixing those additives, the color match, or well, master batch color, or the additives, or both, mixing them into the filament as it comes out. It comes out here. Normally, let's see if they have, they may not have a cooling tray here. Oh, wait, here's the whole setup. Let's look at that one. So now we're at $7,000. Here's the whole setup. I would like to see a bigger picture of that, but I don't think I can. I can see individual ones. But so you've got the extruder side over here. You've got a cooling region in the middle here where you're checking. You may be checking diameter. Normally you're checking diameter over here on the take-up side. But normally it's got to cool, right, because it's a molten-ish material when it comes out. It's soft anyway. So what we did is we just let it fall on the floor at a certain rate to kind of control the diameter. But they do have cooling areas and take-up reels. I think we did eventually build our own take-up reel to help with that. And so, it takes it up at a certain rate and helps control the diameter of the actual filament. And you can create filament. That's basically the process of even the industrial process for creating filament, is that same process just at a bigger scale. Those additives, they are changing the properties of the filament. And if you go to, if you go in here, then I put 3 journal articles. So the Stefan from CNC Kitchen, he did a little investigation of his own, I don't know, maybe a year ago or so, in the past. And he found these papers about influences of just color. So not necessarily any of the other additives like the silk or the matte or antibacterial or whatever, but just color. And he went and got 10 colors from the same manufacturer so that he would be kind of sure that the baseline process is the same. The only difference is the color that's added. And he tested them in different ways. So he tested an impact test, he tested just a tensile test, and a combination loading test where it's kind of a hook that does bending and tension and I guess compression at the same time. I guess no torsion on that necessarily, but try to get an overall rating and see if, just everything else being equal, assumedly everything else being equal, does the color make a difference in the strength of your part? And it did. So some of these papers, I have one of them pulled up. That's not it. This one. So this is one of those papers, and this is some of their conclusions. So this paper is not Stefan, one of the papers he linked. They did 14 different colors. I didn't bother to read their exact experimental setup. I just looked at their summary here. So it's not a long, it's 8 pages, so you can read the whole thing relatively easily. But there. And that could vary a little bit. The color can influence the yield strength, and so it can change the yield strength 36%. So now we're talking about the point where we have permanently deformed our plastic piece, and it's 36% difference. Ultimate tensile strength, that might be one that you're interested in, up to 30%, 31%, just based on the color. Toughness, so that's if you were plotting the stress strain curve, the area under that curve, so it's just an overall general measure. It's not necessarily making it stronger, just tougher. 300%, so that's a pretty big difference just based on color. And then strain, 400%, which kind of explains the big change in toughness too, without necessarily a huge, although 30% in your tensile strength is relatively large. So it's not just that it makes it stronger necessarily or weaker, it's that it affects the whole performance of it. So that's the color. They did say, let's see, I don't know, here they are. Brown and pink have the highest influence on strain. And then they have a chart for there's toughness. Pink seems to have the highest influence on toughness also. There is a toughness on, or a change on ultimate tensile strength. This was the one that was only 35%. Pink is actually one of the weaker ones here, with red being a stronger one. So all of these colors are made from different pigments. So like white is made from titanium dioxide. Let's see, I had written, because I don't remember all of these. Let's see, I wrote down some of the others. Where did I put them? Iron oxides make your reds, browns, blacks. Well, black can actually be made from carbon black. Chromium oxides can make green. The cadmium ones, yellows, oranges, and reds. Ultramarine, which is interesting. So ultramarine doesn't have a name like the others, like iron oxide and chromium oxide and all that. Originally, ultramarine, this is a completely side note. Originally, ultramarine was made from grinding up a blue stone, lapis lazuli, I think. And ultramarine, the actual word, meant ultra, beyond, marine, sea. So it was beyond the sea. They actually had to import the rocks, the lapis lazuli rocks or minerals, whatever they are. Had to import them, and they became ultramarine because they had to import them across the sea. And now you don't do that anymore. Now, or I guess you could, but now it's a synthetic material that does the ultramarine color. Anyway, that makes blues and those shades. And so it could be that it's a big effect, pretty large effect on toughness. But there could even be an effect on strength. Here's yield strength, also with the reds at the higher end. Reds and blacks at the higher end of tensile strength, which kind of makes sense if yield strength is also higher. But they're at the lower end. Well, no, black is in the middle. Red is towards the lower end on toughness. So that means there's not as much area under their curve. So they don't stretch as much. Once they get to their ultimate strength, they're going to fail, basically. Their ultimate strength is just higher. So that's an interesting paper. The other papers gave similar results. You can kind of see some of their samples that they printed. Now they're just doing 3 per color here. So again, there's they did not, I didn't see. Yeah, they didn't put error bars on here, and they didn't report a statistical difference. They just said, basically did the average. So this report needs to have some improvements on it. Stefan's was the same thing. He did put error bars, but he only did 3 samples of each color. So that's very limited sample size. This would be a good, now to do all 14, that's a lot, but for your technical memo, if you're on campus, we do have some tensile testing machines. If you don't have a tensile testing machine, you can't really do a great, your data is going to be pretty coarse, I would say. But if you're on campus and you want to do one of these type tests, pick 2 colors. Maybe, based it off of one of these. Maybe pick a red and a orange or pink or something, which is odd because orange and pink both have red in them, but orange is also going to have yellow and pink is going to have white. So that's interesting that red by itself is actually one of the stronger ones, but you mix in another colorant and it becomes one of the weaker ones. Anyway, so that would be an interesting study. Pick 2 materials and see if you can detect some of the differences on a larger sample size. So maybe do 10 samples of red and 10 samples of orange or something, and see if you can also get the same difference, and it's statistical at that point, or at least it could be statistical. You'd have to do a t-test with the smaller sample size, but you could at least do that. 3 is really small. Okay, make sure there's nothing in the chat. I haven't been looking at it. There's not. All right. Other things that can be affected that would be harder to test: UV stability. So it's possible that the additive, some of those additives in the color match, or not color, but the additive section here, they were UV stabilizers, UV absorbers. You could just have the color. So like if it's a darker color, like black or dark gray or maybe even a dark brown, it's going to absorb light more because of its color, just because of its color, not because of any additive, but just its color will absorb light more, which will heat it up more, so that you'd have to be worried with that. But it could absorb the UV before it gets to the inner parts of your print, and so maybe you have some UV absorption just by the color of the material. None of these papers that I saw actually did anything with UV stability. The grain size of these resin or these additives, they could be they could create little tiny stress concentration factors. They're not like it's not like a thing that dyes the material. They're mixed in and they remain their own little particles. They're just spread out through the filament and color it. So they do remain as little, 100 micron or maybe not. No, that's probably pretty big. I don't know. They're probably in the couple of 100 nanometer size particles that are interspersed in your part. And this is something we noticed on the ground tire rubber thing, is that now you're talking about physical. These were like 100 micron pieces of rubber, and they get embedded in your filament, and so that decreases the strength of the filament because you've got these essentially voids. It's just a rubber piece that's stuck in your filament, scattered all throughout it. So it does decrease the strength because they don't add any tensile strength really to the part. So these additives can change that. They could create little micro stress concentration factors because they're little points in the part. They could create micro fractures, so you could have some fatigue issues. So they can do a lot of different things to your part that you've printed with this filament that might have these additives. I don't know what the silk additive is. This company had a shiny silk finish. So I don't know what it is that creates the shiny effect, but it does seem to have a pretty significant effect on strength, or at least layer adhesion. So any of the strength related to layer adhesion, it seems to really reduce layer adhesion. So those are all things that could deserve more in-depth studies. And I didn't go look and do a current. These papers were like 2019, stuff like that, so they're not old. But I don't know of any broader studies with larger samples of that. So that'd be an interesting thing to do. I've scrolled across this little picture. So this is actually one thing that's not far from stuff you could do relatively easily, particularly if you had a broken Ender 3 type printer. So this is some homemade PETG filament from a Coke bottle. Well, it's clear, so yeah, I think that would probably be a Coke bottle of some sort, like a 2-liter bottle, not a glass, but a plastic 2-liter. So we have one of these. I'll try and bring it. It's kind of big, but maybe it's transportable. I'll try and bring it for Wednesday or Friday. But we built one of, where did I put it? Not that, this Recreator. We built one of these. So now this is a fancy version. There's actually some really simple versions of this online that you can find. Basically, this little part in the middle is the hot end off of Ender 3. So you can even see the fan shroud and everything there. It's just turned on its side. It's still on its mounting plate even. So if you have an old Ender 3 that you're not using, you could turn it into one of these. Over here, you've got a plastic bottle. Now it's not quite as simple as just taking a Coke bottle and plopping it down on there. You'll notice that this one is nice and smooth, where most Coke bottles are not. Some of them are. Some of them have better smoothness than like the shape of a Coke bottle sometimes has. So you do have to try and even out the Coke bottle shape, and you do that by hot water or heating it with a heat gun and pressurizing it and letting it kind of make the sidewalls all the same thickness. Cut off the bottom where it's got the little lumps where it sits, and then there's a little knife blade here. I don't know if I can zoom in on. Nope, can't zoom in on it. Can I zoom in this way? Yeah, we can zoom in. Not really. So it's just, yeah, can't zoom. You can kind of see it coming out here. It comes out of this little strand, goes into the hot end. So it just goes straight into your hot end. This nozzle, you can kind of see it there shining. It's been drilled out so that it's 1.75 output, because that's the filament you want to make. And so it's got a, I think there can be a fan. You can add a little fan here to try and cool it down. And then there's a take-up reel that winds it on your spool. And you get, relatively reasonable filament as a result. So you can do that yourself with much simpler than this setup. This is the Recreator 3D. You get, here's a smaller version of it. But there are DIY versions that are even simpler than this, where it's basically pulling filament through a hot end. Pulling not filament, but pulling a little strip of PETG. These bottles are usually PETG. I guess it didn't say that. So you can make your own PETG filament. So if I can remember and am able to do it, I'll try and bring ours so we can look at it and maybe run it and see if we can get some filament to print with. So you can recycle that way. You might have heard PLA is biodegradable, and that's technically true. PLA is made from the sucrose from like corn, turned into dextrose, turned into lactic acid, turned into polylactic acid. So PLA is polylactic acid. So it is a plant-based product. For a kilogram of PLA, it takes just under 3 kilograms of corn, for instance. So it's not a great ratio there. So 3 kilograms of corn gives you a kilogram of PLA. You don't have to make it from corn, but that's just the crop that it a lot of times is made from, if it's made from a crop. So it being made that way does mean that it can be biodegraded. But if you just took your PLA part and put it outside and expected it to turn into compost or something in the next couple of weeks, that's not the case. So the way it actually works is it is biodegradable, but it would take 80 150 years for it to just sit outside and biodegrade. So it's really not making any difference on the multitude of plastic waste if you just are thinking it's going to go outside and degrade. It can be biodegraded in a industrial type facility. In a couple of weeks, you could probably get it to biodegrade, but there just aren't many of those facilities. The problem with PLA and recycling is that, or a problem with it, is that you can't really mix it in with the other recyclables. So like ABS stuff, it's categorized as a number 7, which means that it's not really mixed with other stuff. It has such a low melting temperature that if you put it in, try to mix it with ABS with a much higher melting temp or glass transition temperature is what I should say. The PLA melts so much lower then it becomes kind of like a contaminant to ABS. So it has to be done on its own, all PLA by itself. And so there just aren't many facilities that do that. You can create one of these type of things for PLA, but now the problem is the thing that makes this recreator work is that you're specifically using bottles that you can slice into little strips. If you're thinking you're going to take your PLA part and it was a failed print, throw it in here, it's not going to do this. So there's another step. You have to go more like this route. And I wonder if they have a chopper here. Yeah, so you need something like this. $4,000 here. Reclaimer here, $8,000. You have to have something that's going to chop up the part into something like these little pellets, wherever we had them. I don't remember where we had the picture of the pellets, but you won't make the pellets themselves, but you can make little chopped, something like these pellets. And so you have to chop it up. Maybe some people use, and this is what we actually used in when we were doing our Philobot, making our ground tire rubber. We actually used a paper shredder. So you can. We had to out the other end of this filament. You have to chop it up somehow. So you have to do that. You have to have one of these screw extruder type things. You can't just pull it like the recreator. The recreator is just, this take-up reel is just pulling it all through here. There's nothing being pushed through like the extruder auger on one of the other type of filament, the industrial type of filament makers. Here you're just pulling this little strand through. So it's a little bit harder process to do on your own because you have to chop it up and you have to send it through something like one of these setups. And well, this one's way more expensive than what a consumer is typically going to buy. You're not going to make that much filament, I don't think. So it's a hard process to do. It doesn't decompose on its own really any differently than plastic. It does, but it's 80 years, 100 years to decompose. There aren't many facilities that change this stuff out, recycle it. And there's a little bit of an issue on the additives that might be in it. They may not be nice to recycle sometimes, depending on what they were. So PLA is not like, it's not you're not using it just because it's biodegradable, it's made from plant products. Those are all true, but they're not true in the sense of you're making much difference. The reason to use PLA is because it's easy to print. It is less harmful than some of the other materials you can can be released as nanoparticles during printing. It's one of the better materials though. It has the lowest amount. You don't want to have a room full of printers that's a small confined space, low air circulation, and you're in that room. You don't want to have that even with PLA. I assume most of you have a printer, maybe two. And even then, I don't know if I would want to constantly be next to the printer as it's printing, just because they do release nanoparticles from the material that's as it's being heated and extruded. It's probably at the scale of 1 or 2 printers. I don't think that would ever really affect you. With PLA, some of the ABS and some HIPs, and there are some materials that I wouldn't want to be around printing really at all, unless they were enclosed and ventilated. But PLA, it does have some particle emissions during printing, but they're very, very minor. And you would have to have a lot of printers in an enclosed space for it to aggravate most people. Now, you might have a sensitivity to it that other people don't have. Let's see. I did have this pulled up. You can buy, at least I found one source on Amazon, for the additives. So, the color additives anyway. So, they had a selection of different color additives. If you had a way, you had one of these filaments or whatever, or you had made your own, then you can actually get the raw pellets. These are not the raw pellets, these are the additives, the color additives. But you can get raw PLA pellets just like these, just they're PLA instead of the color. And you can make your own filament. I have not, other than the research type filament we've made, and this one piece here of PETG, haven't really made my own filament for any real reasons. But I thought that would be a little bit interesting on how the filament is made, stuff that gets added to it. The stuff can affect the performance of your parts. It can make them weaker. I don't know that there's a particular, well, I guess none of these are studying like the carbon fiber that potentially could strengthen your part. These are all making the parts weaker in some way. It's just some of them make it less weak. Adding color is not going to make it stronger. For instance, like if we just had the bulk material, it should be stronger than any of these, just PLA by itself. So if you're interested in doing one of these studies for your technical memo, let me know and we can set you up with the testing machines to actually record some data. There are specific test sample sizes. You'll notice, I don't think I used this class. I think it's another class, but there are ASTM. These are ISO, but they're the same standards in ASTM for particular shapes that you make, in this case print, when you're trying to test a material. So this is the ISO 527-2. Which is probably it's probably not specifically for 3D printing. It's probably just the specimen shape for a plastic part that you want to test, tensile test. All right, I will see y'all Wednesday. Hopefully I'll have my sound worked out where it's not doing this. I'm not sure what happened to my normal speaker. And if I can get it, I will bring our filament extruder here and we can kind of see how that works in person. Not the Filabot, but the Recreator. Maybe I could get the Filabot. Not sure if I could get that one. That one's more of a university property, where the Recreator is just a project we made. All right,